again in this advanced conduction lecture series. So this is the lecture 12. So firstly, let me briefly recall about the previous lecture. So we were on the way of solving the problem of an one-dimensional unsteady state heat conduction in a slab, right? So in last lecture, I told you about the principle of superposition and when and where we can apply the principle of superposition. That I also told you. That is, the differential equation, that is the governing equation, must be a linear one, right? Okay, so now let us apply the principle of superposition and solve the problem. So today is lecture 12. Lecture 12. Okay, so we have to apply the principle of superposition. So there is one rule that you have to keep in mind before breaking the problem, right? That is, the logic was that because we can apply the superposition problem, that is why we can break the problem. Because if we have the solution theta 1 and theta 2, then theta 1 plus theta 2 is a solution. And here we have to find that final solution theta 1 plus theta 2. We will break the problem into two problems having two solutions theta 1 and theta 2. And now we will see that how to break the problem. So there is one very important rule that you have to keep in mind when breaking the problem. The rule is, so break the problem in such a manner that governing equations of all the broken, or you can call it all the small or all the sub problems, anything you can call it. Governing equations of all the broken or some problems should provide the governing equation of the real problem after addition, or I should pose the statement like this, that summation of governing equations of all the broken or small problems should provide the governing equation of the real problem, and the same should be followed by the boundary conditions as well as initial conditions. Okay, so this should be maintained. Now, what does this statement mean? So let us see that. So here, firstly, we again write the non-dimensional governing equation and the boundary conditions. So let me write those things again. Okay, so let me just find those and I will just copy those things. Okay, so I think not this one. Okay, this was the thing, right? So I will minimize this and then I will copy the thing. Copy, again maximizing it, and then I will paste it. Okay, so I have to place it correctly. Yes, now it is done. So here our unknown variable is theta, right? So let us take theta equal to theta 1 plus theta 2, let. Okay, so this is the solution of problem 1, and this is the solution of problem 2. Clear? So what this statement written in this blue ink means is if we have the governing equation of problem 1 as f of theta 1 equal to 0 and problem 2 as g of theta 2 equal to 0, and if my actual governing equation can be written as capital H of theta equal to 0, if it is so, then I must have f plus g equal to h equal to 0. Okay. Similarly, if my boundary condition is given by some f1 of theta 1 equal to 0, or maybe anything not 0, maybe any other function like maybe your f f f prime, and my g1 of theta 2 is equal to maybe g prime. So this f prime and g prime, these maybe are constants, and these can also be some functions of theta 1 and theta 2. And if my boundary condition for theta is given by h1 of theta is equal to h prime, then I must have f1 plus g1 equal to f dash plus g dash. So here this must satisfy that this must be equal to h1 and this must be equal to h dash. If this satisfies these things that I have explained just now, then I can say that my problem is now broken into smaller problems, and it is mathematically well conditioned. Okay. So now let us try to break the problems. So my governing equation is this one. This is my governing equation, right? So let me write it. So what I will do is I will give two headings. So this is my, okay, so let us do it like this: problem 1, and in this side I will be having problem 2, right? Okay, so it will be better if I also write the problem 3, then okay, so problem 2, and here I will be having problem 3. Clear? Okay, so problem 3 is what, or maybe I should write actual problem, then this will be accurate. Actual problem, correct. Now actual problem is what? Actual problem is your del 2 theta del x bar 2 is equal to your del theta del tau. Okay, is my mic on? Yes. Now you see I can break this problem like this. Now during breaking the problem you should keep in mind the purpose of breaking the problem. So what was the purpose? That is because I have two homogeneous and two inhomogeneous equations. So had I had three homogeneous equation and one inhomogeneous equation, then I did not have to break this problem into smaller problems. So what I have to do is I have to break the problem in such a manner that I can get one problem with three homogeneous equation and one inhomogeneous equation, right? And I have to see that what could be my other problem, so that I can get the summation of those two smaller problems is equal to the actual problem. Okay, so I think this is a bit hard to understand, so let us see. So if I write my solution of problem 2 is theta, okay, and my solution of problem 1 is, so let me take some other color, maybe yellow. This is theta 1 and this is theta 2, okay. So this is theta 2 and my actual problem is having the variable theta, okay. So first of all, my theta 1 plus theta 2 is equal to, okay, let me use the appropriate colors, then it will be embedded into your mind. Theta 1 plus theta 2 is equal to theta. So this is what we have to, I mean, this is how we have defined the smaller problems, right? So don't work with the similar variables. I mean, these are the some silly mistakes which we make during the exams because of the exam environment, right? I mean, don't take theta for all the smaller problems. That will be totally incorrect. Okay. So I can write, maybe this equation is, okay, theta 2 is equal to 0 and, okay, that is my theta 2 is not a function of tau, okay, and I can write here del square theta 1, okay, this is equal to my del theta 1 del tau. Clear? Now you can argue that how I am getting this equation, this equation by adding these two, because if I add this and this, then I will get del 2 del x bar 2 theta 1 plus theta 2, and then I can write it as my del 2 del x bar 2 theta, because this is equal to theta. But how I can write this plus 0 equal to this? See, I can write this 0 as del theta 2 del tau, right? The moment I can write this as my del theta 2 del tau, now you can see by adding this and this, then I can get this. Clear the logic? So it is done. So this is the governing equation. Now let us write the boundary conditions. So this is a steady problem, okay. So first let us write the initial condition then, okay. So for the unsteady problem, the initial condition will remain same. So let us revisit the initial condition. So it was theta for the whole domain, that is this, and for tau equal to 0 at initial time, this is equal to what? So this is equal to our, there was a given expression, this one, it is Ti minus T1 by T2 minus T1. So this is Ti minus T1 by T2 minus T1, right? And this is obviously theta 1, okay. And my final expression is what? My final expression is theta for the whole domain tau equal to 0, I must have this one. Okay. So here now what will be this, right? So first of all, this theta 2 is not a function of tau that I have defined, okay. So if this is not a function of tau, that means theta 2 will have a particular solution, okay, that will be a function of x bar only, and this solution is valid for all tau, right? So see, this is the solution that we will obtain for theta 2. Now again you can argue, then my breaking of the problem is not okay, because if I add this equation and this equation, then how I am getting this equation? Because here if I add this theta 1 and theta 2, then okay, I am getting theta, because that is my definition of theta 1 and theta 2. But if I am adding the RHS, that is this one and theta 2, then this is a constant and this is a function of x bar, and which is a non-zero function. Then how I can get by adding this to only this one, because there is another extra term this. So to have that, I have to modify this condition. How? So just think that what should be there so that I can add this and this one to get this one. So there, if I am having, let us say that, okay, now I know that this will not be the case, because if I add this and this, then I am not getting this, right? And the moment I define that my theta 2 is not a function of tau, then I cannot play with this solution, right? Okay, so now if there is a x that we don't know, that what should be the RHS of the initial condition of this problem 1, that we don't know, but we know that x plus theta 2 of x bar, that must be equal to this. We know that, correct? Then my x must be this one. This is my x. So this should be my RHS of the problem 1 for the initial condition. RHS of the initial condition for the problem 1. So let me write it clearly. So have you understood the philosophy? That is, you first know the purpose. That is, I will have one equation retaining this unsteady term, but if I am retaining this unsteady term, then I have to ensure that I will have only one inhomogeneous boundary condition, and here I will not have. Okay, so let me complete and I will re-dictate this thing. That is the main philosophy. So this should be this minus theta 2 of x bar. This is my initial condition for problem 1. This is my not initial condition, but this is valid at any time for my problem 2, and this is my initial condition for actual problem. Now let us come to the boundary conditions. So the first boundary conditions, that is theta 1 at x bar equal to 0, right? If I am not wrong, so let us match. Okay, and this was 0 for the actual problem, right? So let us have this as again 0. Okay, now I will have this as also 0, and then if I add these two, then I will not have any problem in writing this. Clear? Now my second boundary condition is this as 1 for all tau greater than 0. So this will be what? Now see, here this equation is homogeneous, this is inhomogeneous, because I have this term here, and also theta 2 is like a constant for theta 1. This is also homogeneous. Now the purpose of breaking this actual problem into smaller problems was, I must have two equations where I am not getting more than one inhomogeneous equation in any problems. So in problem 1, I have one homogeneous equation and one inhomogeneous equation already. So I cannot have one more inhomogeneous equation. So here I cannot write 1. So here I must have 0. Either I have to have 0 or I have to have some function f of theta 1. So for the sake of generality, so I mean, let us first write that f of theta 1. So now we don't know that what is this function theta 1. Okay, obviously this function cannot include any constant, any additive constant, like it cannot be theta 1 plus c, okay, or 2 theta 1 plus c. The moment I have any other constant here, then it will not be a homogeneous equation. Okay, so let us say that we don't know it, so let me write it at x. Okay, we don't know this thing. This can be some function of theta 1, this can be 0 also. Okay, now here I have the liberty of writing this as 1. Okay, because this is a very well known problem to you guys, right? That is, the governing equation is this and you have two boundary conditions. This is the simple steady state conduction problem in one dimension, right? So then again I know my actual boundary condition here. That is, if I'm having this one, so this is 1. So again the same psychology, sorry, the same philosophy, that is x plus 1 should be 1, that means x must be 0. So here this will be 0, okay, this will be 0. So did you understand the whole philosophy, that how we broke the two problems? So let me again explain this. So the main problem was that we cannot apply the separation of variable here because we were having in the actual problem two inhomogeneous equations, this one and this one, right? So our purpose is that let us break this problem into two more problems in which none of the problems should have more than one inhomogeneous equation. Okay, now how I broke so quickly this problem into these two problems, that is because I have experience. Okay, so firstly your job will be, so let me define a new variable theta 1 that will satisfy the same governing equation, okay, but it will have only one inhomogeneous equation. So first you do something, that is, you will not write this equation, but you will write this governing equation and this equation. So the moment you write this one, so then you can get this one by subtracting this equation from this equation. You understood what I am saying? I am saying that you told yourself that let me define a variable theta 1 that satisfies this governing equation only. So then you got this equation, then you could have here this equation as this plus del theta 2 del tau, because your mind will say that okay, if I am subtracting this equation from this, then I will have in the RHS this one. That is okay, there is nothing wrong about it. Now you come to the first boundary condition. You see the first boundary condition is already homogeneous, so I don't have any headache regarding the first boundary condition. But the second boundary condition is having an inhomogeneity, that is this one. That is why I am bound to put here either 0 or any theta or any function of theta 1, maybe theta 1 square, maybe 2 theta 1, anything, but no additive constant should be there. For example, theta 1 plus 3, 2 theta 1 plus 4, this 3 or 4 should not be there. So you put here 0 for the sake of the simplicity of the problem. You put here 0, then you must have to put here 1. Then you got this and this. So the initial condition is only thing that is remaining. Now you could have put here del theta 2 del tau, okay, that is, you are saying that my theta 2 is also a function of tau, that you could have done, okay. But then see, if you have written here that this is my x, and then you could have written here that this should be what if my theta 2 is a function of tau again. Okay, if my theta 2 is a function of tau, then how I can write this? Then you could have write your initial condition for theta 2 as this tau equal to 0 as 0, because 0 plus this one is equal to this one. So that is also a correct breaking of the problem. But again, now you see, no, that is okay, because there is 0, there is no problem. You understood? That is, if I had written this one here, then my theta 2 is a function of tau again. Okay, so then my question would be that if my theta 1 has this in RHS and my theta also is having this in RHS, then my initial condition for theta 2 is this one. This is 0. Okay, so that will be also a valid breaking of the actual problem. So I hope you have understood. So these things actually you have to develop by your own, by practicing more and more problems. I am trying my best to convey you the philosophy that how you should break. So let me please know in the comment box that if you are able to grabbing the concepts or not. Okay, because if you are not grabbing the philosophy, then if anyone is modifying the problem by anything else, then you will not be able to break the problem. If you just mug up the problem, yes, if this come into exam, then I have to break this and this into this and this, but you don't know that how to break it and why I am breaking this, then you will most probably will make a mistake in exam. Okay, so this understanding of this philosophy is very important. Okay, so now let me go for the solution. So now it will not take so much of time. So first let us solve the problem 2. Okay, problem 2. So can you see these three things in one screen? So just for a moment, let me minimize the screen and just visualize this problem 1, 2 and the actual problem. So this plus this should be equal to this. So this plus this should be equal to this. This plus this should be equal to this, and this plus this should be equal to this. This was the statement written in the blue ink at first. Okay, so you just take a look in the three problems. Okay, now we will solve first theta 1 and theta 2, then we are done. Okay, so problem 2, I don't think I have to solve it again. It is an one dimensional steady state conduction with no heat generation. Right, so this is your homework to solve it. So let us say that we know this solution as theta 2 is equal to theta 2 of a and which is a function of x bar. So now let us solve the problem 1. This is the main challenge. Okay, now some of the steps I have already done previously, so I will do it very quickly. Okay, so here I will solve it by method of separation of variable. Okay, so separation of variables. So I will call it in short SOV. So I will have let my theta 1 is equal to a, that is only function of x bar, into b, that is only a function of tau. That means I will have, if I put this in my governing equation, so then I will have my b into d2a dx bar 2, d2a dx bar 2 is equal to a into db d tau. If I further manipulate it, then 1 by a d2a dx bar 2 is equal to 1 by b db d tau. Clear? So this is a sole function of x bar only, and this is a function of tau only. The only possible option is a constant. Okay, and this I told that this is a separation constant. So all these steps I have done before. Okay, and I also told that this mu s must be negative, so I say that this is equal to lambda square, where this lambda cannot be equal to 0. Okay, because mu s cannot be equal to 0. So this is the thing. So now let us first go for this one, that is 1 by b db d tau is equal to minus lambda square. So I will directly get b is equal to some constant c e to the power minus lambda square tau. So let us mark this equation. Okay, and let me call this equation as equation 1. Clear? Okay, so now let us go with the another equation, that is 1 by a d2a dx2 is equal to minus lambda square, and that is equals to d2a plus lambda square a is equal to 0, and I showed you that this will have a solution of a is a function of x bar only, so this will be some c1 sine of lambda x bar plus some c2 cos of lambda x bar. Clear? Okay, so now I have unknown constants here c, here c, here c1 and here c2. So firstly let me number this equation as 2 and let me box it. Okay, so now apply the boundary conditions here. Okay, so see, a is a function of x bar only, so the x bar dependence of theta is actually coming from a. Okay, because a is the function that is making theta 1 as theta 1 x dependent, right? So the boundary conditions which are which are for x bar only, x bar variable only, that will be applied on this a. Okay, so we had the boundary conditions theta of x bar equal to 0, theta 1 of x bar equal to 0, right? Obviously there was a time also, tau greater than 0 is equal to 0, and also this one x bar equal to 1, tau greater than 0 is equal to 0. So here we will directly write, that is a of x bar equal to 0 equal to a of x bar equal to 1 equal to 0. Okay, these were the boundary conditions where the x bar was the determining variable. Okay, so let us put these boundary conditions into this equation. So if I put the first one, okay, so a of x bar equal to 0 is equal to c1 into 0 plus c2 into 1 is equal to 0. That means my c2 is equal to 0, so, right? So that means my A is equal to C1 sine of lambda x bar only. Now I am applying the second one, that is x bar equal to 1 is also equal to 0. That means my C1 sine of lambda is equal to 0. So now you see, if I have to satisfy this equation, then I have two options, right? So one option is my C1 equal to 0, another option is my sine lambda is equal to 0. So if C1 equal to 0, then so if I follow this one, so if C1 equal to 0, then my A is coming as 0, right? Then my theta 1 is coming as 0, which is a trivial solution, right? Which is a trivial solution and which we don't want. So we will approve this solution. So my sine lambda is equal to 0. Okay, so this is actually this is called the eigen equation. Okay, eigen condition, not equation. So I hope that you have already heard this term eigen. Where? In the linear algebra, right? So in linear algebra we learn about the eigenvalues and eigenvectors of a matrix, right? So this is also an eigenvalue problem for a differential equation. So here this lambda is the eigenfunction, okay, and this is the eigen condition. So I mean, this is defined like this. Okay, so there is a eigenvalue problem in linear algebra also. Similarly, there is an eigenvalue problem in differential equation also. Okay, so here then from this equation my lambda is the integer multiple of pi, right, plus minus n pi. So I will take only the plus values because the solution here, my A, if I take plus lambda and if I take minus lambda, okay, so firstly, so let me tell you, this is my lambda subscript n, okay, so this is the nth eigen function. Now why I am taking this n, I mean this plus n only and not minus n? So because now you see my a n, that is a function of x bar only, it will be some c n into sine of lambda n x bar. Now if you put here lambda n equal to plus n pi, so then maybe you are having some c n dash. So this is for lambda n equal to plus n pi. So let me write it. So for lambda n equal to plus n pi, you will get c n dash sine plus n pi x. For lambda n equal to minus n pi, you will have a n equal to maybe c n double dash. I mean the constant will be different. Okay, and this will be sine of minus n pi x bar. Okay, so now see, this is also a solution and this is also a solution. Then for the general solution, I have to actually, I mean for n equal to 1 to infinity, for n equal to 1 to infinity, all the an, these are the functions, all the an functions are the solution. So for the general solution, I have to add them up. Okay, now during adding, see this minus will come here and I will get a new constant as cn minus cn double prime, and this will be only n pi x bar. So I can term this as a new constant c triple prime, and that is why I am just taking the n only. Have you understood this? That is because for every n there is the, I mean for every n, an is the solution. So the general solution is summation of that. This is the same concept when you learn your general solution in for trigonometry in your 12th or maybe 11th. I don't remember exactly. So that is because that is all the ANs are solutions. So for the general solution you have to add them up. Now the moment you add them up, this minus will come outside and I can take this C1 prime and Cn double prime common, and I can write Cn prime and Cn double prime into sine n pi x. So this is another constant, C triple prime. That is why I am not taking the minus 1. Okay. So believe me, none of the professor in no IIT, I should not tell like that, but I hope in most of the places, nobody explains in these details because they expect you to guess or to learn these things by your own. This much maturity they expect from you. Okay, but here I am not expecting from you anything. So that is why I am trying to convey you the most basic thing also. So please just let me know in the comment box if you are okay with these concepts or not. If you are facing any difficulties, please let me know that where you are facing the difficulty. So I think already 41 minutes are there. I cannot afford much time, so I have to wrap it up quickly. Okay, so my AN is this. This is my AN. I can now box this. Okay. Therefore, my theta n, that is a function of x and tau, that will be equal to AN, that is a function of this, into Bn, that is a function of tau. Now why I have written Bn here? Because see, our solution for B, this also contains lambda. So because lambda has multiple values, so that is why this B will have also multiple values. So here actually I should have write now B of tau, Bn of tau equal to maybe some C dash n, because Cn I have already used for my A, and this is lambda n square into tau. Okay, so now let me put these values or the expressions I should say. So that this is Cn into sine lambda n x bar into, so now this is C dash n into e to the power minus lambda n square into tau. Clear? Now I can club these two constants and I can write any other name. So let me term as Kn. So Kn sine lambda n x into e to the power minus lambda n square tau. Now for every n, theta n is a solution. So my general solution is theta is a function of x comma tau, x bar comma tau, is equal to summation of theta n, that is a function of x bar comma tau, n runs from 1 to infinity. Okay, where now here this lambda n we know as n pi, right? Okay, so now what are the only unknowns? So here I have unknowns as this Kn. Okay, so this is the unknown, right? This is the unknown. So how to find this? So now can you tell me that for problem 1, which condition or which equation is still there to be used? That is the initial condition, right? That is the initial condition, and the initial condition was this one. This was the initial condition. See this one. So let me write this. So initial condition is is my theta x for all x actually in the domain, and for tau equal to 0, that is equal to my Ti minus T1 by T2 minus T1 plus minus theta 2 of x bar. So just keep in mind that this has been already found. Okay, so this is already found here. This is your homework, right? Because I mean, this is nothing but your graduation level thing, your B.Tech or BE level thing, right? So now I have this. So put in this equation, so I have theta equal to this, right? So now theta at this for all x and tau equal to 0. Now you put tau equal to 0 in this equation. Okay. So that is, so I am writing, I will try not to jump any step. Okay. So this is a function of this one. So tau equal to 0, and now I know that my theta n is equal to what? Some kn into sine n pi x bar, n pi was the lambda n, into e to the power 0, because I was having what? I was having e to the power minus lambda n square into tau. So I am putting this tau equal to 0. So then this whole thing boils down to 1, right? So this is equal to what? This is equal to Ti minus T1 by T2 minus T1 by theta 2 x bar, right? So let me term this as any other constant, namely, okay, let me not term this as, I will write, because that can create more confusion. Okay, so now I will introduce you with a very important concept. So just focus. Okay, just keep your mind here for next 5 to 10 minutes. So obviously I hope that you have your mind here only. Okay, so what I will do now, I will prove the orthogonality of function a of x bar. I will prove this. So let us see. So I have this differential equation here, right? A is equal to 0. Clear? Sorry, this is not equal to 0. This is equal to minus lambda square. So for any an, all the ans will satisfy this equation, right? All the ans will satisfy this equation, because I have already told that I got this an by solving that equation, right? Only I got this an by solving this governing equation only, this governing equation only. I mean, sorry, this is equal to this mu s. So all the ans are the solution of this equation. So ans, all the ans, for any an must satisfy this equation. Clear? So now what we will do is, we will, so first let me write it like this, lambda n square an equal to 0. Clear? So what we will do is, we will multiply both sides by am. where m is not equal to n. Okay, clear? Where m is not equal to n. Now we will integrate this, okay, with respect to dx bar, with respect to dx bar. So let me write here dx bar equal to 0. Okay, so we will apply the integration by parts for this integral, where this has to be integrated because we want to reduce the order of the derivative. Okay, so integration of the first function. So this will be the first function and this will be the second function. So integration of the first function will give dan dx bar, and the second function will remain intact. Then we will get this one dan dx bar, and again differentiation of the second function, integration of the. Okay, so we have to integrate in the domain, because the domain is this one, x bar varying from 0 to 1. So we have to put the limits also. So here if we put the limits 0 to 1, and this is also 0 to 1 is equal to 0. Clear? Okay, so I think I have missed another term, and that is plus lambda square n an am into dx bar equal to 0. Clear? Now I can put actually this lambda square n outside of the integral, because this is not a function of x bar. Now you see here, so I will write dan dx bar at x bar equal to 0 into at x bar equal to 1 minus dan dx bar at 0 into am 0, right? So minus the same integral will remain. So now I can club this term and this term, and I can write what, this one and this one, and if I take the minus common, then I will have minus lambda n square an am, right? I will put a second bracket here into dx bar. This integral is equal to, okay, so this is the total thing, and this is equal to 0. Clear? So now you see, I had the boundary condition for any an for x bar equal to 1 and also for x bar equal to 0, I have this, both of these things equal to 0, right? So this term does not exist, it is 0. Okay, so my battery of the phone has already starting to die down, so I have to wrap it up really quickly. So now I have this equation as, so this is my only equation, minus lambda square an into am dx equal to 0. Okay, now considering this function to be continuous, okay, this function to be continuous and valid for any dx bar, okay, then only I can write dan dx bar dam dx bar minus lambda n square an into am is equal to 0. This is valid for any am, any m and n, but m is not equal to n. So now you just swap m and n, then what we will get? We will get something like this. So the first term will remain same, right? But the second term here we will have lambda m square an into am. So am into n, but that is same, but still for the sake of understanding. Now let me term this as equation A and this as equation B. Now you subtract equation B from A, then we will get what? Equation B is being subtracted. So lambda square minus lambda n square, right, into am n equal to 0. Clear? Okay. So now you see you have again two options here. One option is lambda m is equal to lambda n. Okay. Another option is am into an equal to 0. Okay. So if I am having lambda n is equal to lambda m, that means m equal to n. Okay. And if I satisfy this equation, this condition, that means if this is satisfied, that means my am to an, sorry, I have done a small mistake. The mistake is I don't need this condition. I think that this will not incur so much confusion. I will just retain the integral and nothing more. Okay. So in the integration only I am doing this thing. I am not omitting the integration. Okay. So integration remains as it is. Okay. So integral this. So now this is 0. If m equal to n, this is one option. So if m equal to n, then lambda n minus lambda n square, this is 0, then this is not equal to 0. I mean, then this is not equal to 0. I mean, actually what I can do is I can take this outside of the integral, this lambda m square minus lambda n square. I can take this out of the integral because this is not a function of x bar. Correct. So just let me check the charge in my phone, otherwise everything will be lost. Okay, 9%. So there is a race between me and the phone, I mean the phone's battery. Okay. So for again, so let me write it like this. I think I have to win the race with the phone, right? Otherwise my 1 hour effort will be lost. This am into an dx equal to 0. So now here you have two options. So one is this is equal to 0 and this directly means m equal to n. So if m equal to n, then this again implies that my am into an dx bar is not equal to 0. But if my this thing is not equal to 0, that is my m is not equal to n, then I will surely have this thing as 0. Okay. Okay. So this is the orthogonality condition. So why this orthogonality condition? I will give you a small analogy. So if I can remember it in the next video, then I will explain it in a more elaborate way. See, if I have two vectors, when I can say that those two are orthogonal, when the dot product is 0. So this thing is kind of a dot product. This is called the inner product actually in the function space, or the that is also called the Hilbert space. Okay, so in the Hilbert space or the function space, this is the inner product of two functions, and this is analogous to the dot product for two-dimensional vectors. Now for two-dimensional vectors, if I take the dot product and if that is coming to be 0, then I say that those two are orthogonal. Now here also you see that if I am taking a dot a, I mean if I am taking the dot product of two same vectors, then I will never get 0. But if in an orthogonal coordinate system, that is I, j and maybe k, if I am getting I, j, k, then I dot j equal to 0, I dot k 0, I dot j dot k 0, but I dot I is non-zero, j dot j is non-zero, and k dot k is non-zero. Similarly, if I am having am into am, that is m equal to n, then I will be having a non-zero. Okay, so here this is actually equal to am square equal to an square, because m equal to n. But the moment I am having m is not equal to n, it is having the same significance, that is I is not equal to j. If I am having I dot I, then it is non-zero. Similarly, if I am having am into am or an into an, and that is m equal to n, then it is non-zero. But moment I am having I with another vector that is not equal to I, then I am having 0. So here it is also having 0. That is why pulling the same analogy, I can say that this is the orthogonality condition. Okay, so I am just writing the orthogonality condition. So this dx bar 0 to 1 is not equal to 0 if m is equal to n is equal to 0 if m is not equal to n. Okay, so let me again check the charge. 7%. Okay, I can do it. Okay, so this is the orthogonality condition. Okay, in the examination you don't have to prove this, but this should be proved. Okay, up till now I have not done anything that is beyond basic integration and differentiation. I mean, have I done anything? Had I? So that is the basic psychology or philosophy, that is your objective is to solve any problem that you face in your life in the most simplest way that is possible. So here I have not used yet anything other than basic integration and differentiation, right? So if I apply the same, now go back to this equation. Okay, go back to this equation. So this equation told me, so I need to work with this equation. Okay, let me copy it and I will paste it here. So I have this equation. So continuing, what I will do is I will multiply it with sine m lambda x, sorry, m pi x bar. Okay, in the both side. So this is actually what? This is an and this is what? Am. Okay, and I will integrate it with respect to dx 0 to 1 again. Now I call this as a constant, so let me term this as s. Okay, so s is this one only. Okay, so this will be nothing but my s dx. Okay, integration 0 to 1. Obviously my x is a function of x bar because my theta 2 is a function of x bar. Okay, so now you see what I can do is I can firstly okay, so this is for n equal to 1 to infinity. You see, for any m and n, all these terms, so if n equal to 1 and m equal to 2, So then this integral, okay, so let me go step by step. First of all, I can put the summation out of this integration, because the summation is over n and this integration is over dx. So I can write this thing. So this is sine n pi x bar and sine m pi x bar dx, that is equal to our s dx, integration of that. So now you see, for any n n equal to 1 to infinity, if n is equal to m, then only this term exists, otherwise this term does not exist. So I can directly write this as my summation kn, okay, summation kn sine square n pi x bar, because I am writing here m equal to n, because if m is not equal to n, those terms in this summation will not exist. Did you understand? If m is not equal to n, then all those terms having m not equal to n in this summation, so this summation will have many terms. So those terms which will have m not equal to n, those will not exist. Only those terms will exist for which m is equal to n. So that is equal to, obviously integration must be there, and now I don't need any summation, because all other terms in the summations are no, I need the summation, because still I have the n, sorry. So okay, so then you see, okay, no, I don't need the summation now, because why I don't need the summation? So there is a particular value m here. So here, so my tab is also showing low battery. Okay, so here, and my phone is showing what? Okay, now it is SOS time, that is, it is 5% charge. So my n is equal to a particular value m. Okay, so n equal to 1, n equal to 3, n equal to 4, dot dot dot, n equal to m is a value, dot dot dot, infinity. So all other term vanishes. For all other n, those will vanish. Only this n equal to m will remain. You understood? So this summation will be for n equal to 1 plus will be for n equal to 2 plus n equal to 3, dot dot dot, plus n equal to m plus dot dot dot, n equal to infinity. So all these terms other than only n equal to m, those will vanish. So all this total summation will be kn. So actually I have not practiced anything before teaching you. That is not a very good thing actually, but still I don't have so much time. I mean, I have also my own projects and all things, so that is why these small mistakes are happening. But because I am applying my common sense only, that is why I am able to catch these mistakes. So this is dx. So this is a very easy integral. This you can solve by yourself. Now this is, and this will be a also very easy integral. This, because this s is nothing but your some constant minus theta 2x. Okay, so if I write the term of x, so this will be ti minus t1 by t2 minus t1. Okay, so minus theta 2. Okay, so minus theta 2 is a function of x into dx bar by integration of sine square n pi x bar dx bar. Clear? So see, this is kn, and here also I am having this n here. Okay, so I have found all the kn. So if I have found all the kn, now my theta n is known. So the moment my kn is known, that means my theta n is known, and theta n is what? kn into sine of n pi x bar into e to the power minus lambda n square x bar, right? The moment I know my theta n, I know my theta as summation of theta n from n equal to 1 to infinity, that is theta 1 actually, and I know my theta 2 also. Theta 2 is my theta 2 of x, this is actually theta 1 of x bar comma tau. The moment I know my theta 1 and theta 2, my theta is equal to theta 1 plus theta 2, right? I have completed the whole solution. Now your homework is find theta 2, find the accurate value of kn. Accurate value means no numerical value will be there, there will be an expression. Find the exact expression for kn, find the exact expression for theta 2. I mean, without finding the exact expression of theta 2, you cannot find the exact expression of kn actually. So after finding the exact expression for theta 2, you find the exact expression for kn, thusly you come to the exact solution of theta, okay? And if you have done that, you just put that in the comment box that yes, I have done that. And please put the suggestions, put the feedbacks in the comment box that how is the lecture series going, because I really think that there are some basics which we still need to convey the students, because not everyone is coming from the same background, right? So there is still time to regain the concepts, to relearn the concepts, so that we don't have to face the difficulties in the future, okay? So today I don't have to say much anything,